Okay, yeah, welcome everybody to today's seminar on automorphic forms. So it's a pleasure to have Andrew Phillips from Idaho College, and he'll talk about Gross-Zagier formula on singular moduli for Shimura curves. So Andrew, please.
Okay. All right. So I just want to start by thanking the organizers for inviting me. I was kind of glad to talk about this paper. I mean, I've had this paper around for a while. Like, to be honest, I wrote this about 10 years ago and in graduate school, and I uh, just more recently wanted to see if I could get it published. So I kind of put that out there, and so there's some interest in it, and I'm glad to be able to talk about it. It's always interesting, I think, to go through a paper and kind of try to distill it down to like one hour talk, which is generally not so easy. So this is what I could do. Some of the stuff I have to be, I can't go over the obviously all the details, everything, but it's I did what I could to kind of summarize things. Hopefully, I can give you a good idea of what's going on in the paper. Okay, so so just to start out here, what is the hold on, what is the Gross-Zagier formula? So in general, when people talk about the Gross-Zagier formula, they're usually talking about one of two things. One formula is this relation between heights of Heegner points on a Jacobian of some modular curve in relation to some derivative of an L series. That's probably the most famous one. That's not the one I'm talking about here. The one I'm talking about here is on their paper called On Singular Moduli, which is it's some factorization of differences of J invariance. So the setup for this one is we have two imaginary quadratic fields, K1 and K2, and we're going to assume that they have relatively prime discriminants. So in particular, they're non-isomorphic. And then what we're going to do is fix some representatives of the ideal class groups of K1 and K2. Let's say we have AM and BN. So here the H1 is the class number of K1 and H2 is a class number of K2. And then let's let WI be the number of roots of unity, or I mean the number of, I mean there were three roots of unity, but number of units in each of the KI, which are obviously finite numbers for imaginary quadratic fields. So what Gross-Zagier looked at is this number, this capital J of D1, D2, which is they take this product of these. So this little j here is the usual kind of modular J invariant. They evaluate that at these kind of representatives of the ideal class group, and they take the product of all those differences, and they raise it to some exponent here, 4 over the product of these two numbers of units. And what they did is they looked at the square of this number, which turns out always to be an integer, and they gave it a prime factorization for this. I'm not actually giving you the formula here because it's not all that significant for what I have to say later on. You can look it up in their paper. It's a very readable paper, and it's there's some, like I said, explicit formula with actual kind of functions. I give it the factors here. But maybe I just want to say a little bit about why this, it's not completely obvious why this is actually an integer, J squared. So maybe I can start out by just saying a little bit about that, which is if you just look at the number in the parentheses, forget the exponent just for a minute here. If you look in the parentheses here, that we know just general fact about J invariance that if you plug in an imaginary quadratic integer, J of, like, for example, this ideal class, this ideal representative of the class group, we get at least an algebraic integer out of it. So we know that this product at least is an algebraic integer. And then you can check that if you take, let's say you take the Galois group of the composite of the Hilbert class fields of K1 and K2, and you apply all the elements of any element of that Galois group to this thing in the parentheses, it's going to fix it because it's basically just if you apply a automorphism to one of these J invariants, it just gives it another conjugate of it. So it fixes the thing inside the parentheses. So we know that the number in the parentheses is at least rational. It's fixed by the entire Galois group, and it's also an algebraic integer. So the thing inside the parentheses is an integer. So the only thing to worry about is the exponent here. And there's only really a couple cases to consider, because if your discriminant is less than -4, then imaginary quadratic field only has 2 units, plus or minus 1. So the only thing to really worry about here is if the discriminant is either -3 or -4, because in that case, for -4, it's Q adjoint I, which you have 4 units. For -3, you have 6 units, the 6 roots of unity. So really the only thing to worry about technically is the case where one of them is -3 for the discriminant. But you can check in that case that the J invariant, so in that case, if you have, let's say like D1 is -3, the class number there is 1, and so there's only one factor in that case for that term, and the roots of unity, you have 6 of them, so you have an exponent of 1/3, and you can check in that case that actually the J invariant is already the cube of an algebraic integer, general kind of fact about these J invariants. So Gross-Zagier gave a formula for this this integer J squared, and it's kind of theorem that many people have tried to generalize to other different situations. So mine is some kind of generalization of this. But instead of focusing on the actual kind of factorization part of it with J invariance, which is kind of, you don't really have much, like there are analogs of that for higher dimensions, but I'm going to focus more on a different interpretation of it. So we can actually view this Gross-Zagier formula as a kind of intersection type formula on a modular curve. So the setup for this is if you let K be the composite of K1 and K2, which since the discriminants are relatively prime, you can think of this either as the tensor product of K1 and K2 or the composite of the two. So if you take let's just fix right now some extension of K, some number field. And if you start with 2 elliptic curves over OL, the ring of integers in L, if we look at the coarse moduli scheme classifying elliptic curves over OK, so this is just, think of this as just you can view it as the affine line over OK because the J invariant gives an isomorphism to just the affine line classifying elliptic curves. So if you look at that, think of that as like a integral model of a general kind of modular curve. Then for these 2 elliptic curves, we get OL valued points of this M, and you can view that as these 2 kind of morphisms from spec OL to M. This subscript of the /OL just means base extension from OK to OL. So kind of OK is our kind of base, spec OK is like our base scheme here, and then we kind of, if we want to, base extend to some larger field. So then we get from these 2 kind of OL valued points, we get these 2 ring homomorphisms from the polynomial ring here over OL to OL just by evaluating the indeterminate here at the J invariant, sending the indeterminate to the J invariant. So then the point of this is that we can look at these 2 morphisms from this spec OL to M, even though they're not closed immersions, we can just through kind of the scheme theoretic image view them as divisors on this affine line here, and then we can look at, okay, what's like the intersection of these 2 things as like divisors? Well, just kind of abstractly, it's spec of this tensor product, which you just kind of work out here. If you take a tensor product of 2 rings like that, where you make OL an algebra over OL bracket X through this J invariant, we get this quotient here of OL mod the difference of the 2 J invariants. So in the end, if you wanted to find, let's say, like if you start with a prime of OL, and you want to find the p-adic valuation here of that difference, it basically amounts to finding the length of the local ring of this affine scheme here at the point P. And that basically is, if you look at definitions of like how you define intersection multiplicity, I'll give you a more precise definition later. This basically amounts to calculating the intersection multiplicity of these 2 divisors on this integral model of this modular curve. So we can kind of view this factorization Gross-Zagier formula we saw on the last slide here as a kind of view it as an intersection multiplicity on a modular curve like this. So this is kind of the motivation for how I'm going to generalize it. And so instead of actually generalizing the kind of factorization formula for the J invariants, which we don't really have in all cases a J invariant anymore when you go to a Shimura curve, but now we can view it instead as kind of an intersection multiplicity. Okay, so the setup for this is the following. So if I want to generalize this from like a modular curve, which classifies elliptic curves, to a Shimura curve, which is going to classify what we call QM abelian surfaces. It's like an abelian variety of dimension 2, but it's going to have one that has an action of quaternion algebra. So the notation for this, for kind of the rest of the talk here, is we start with what's called an indefinite quaternion algebra over Q. So it's a central simple algebra of dimension 4 over Q. Indefinite means it's split at infinity, meaning if you tensor it with R, we get M2R as opposed to a division algebra. The discriminant, this dB, is a product of all the prime numbers that ramify in B, which are the numbers that when you tensor B with QP, we get, again, now a division algebra over QP as opposed to M2QP. And then it has this usual kind of involution that all quaternion algebras have, which I'll write as X maps to X iota. And then we fix maximal order of B. Just point out here, if you have an indefinite quaternion algebra over Q, any two maximal orders are going to be conjugate by elements of B cross. So it's all maximal orders are actually isomorphic, some consequence of strong approximation. So we're just going to fix one of them. It's kind of not too bad to just deal with one of them here. Let me just point out, I do allow the possibility that B is split, meaning B could just be M2Q. And then if you take that kind of degenerate case here, we do get to kind of something interesting. I'll talk about that in a minute. So also we fix an element of OB that squares to negative the discriminant. Just point out that there is always such a thing because if you take Q and you join square root of negative the discriminant, that always embeds into this B, just basically by looking at how splitting works in a quadratic field. And then we define one extra kind of involution here. This is pretty traditional to call this X star, X maps X star, where we kind of conjugate the standard involution by this element. And then I'm going to fix throughout an ideal here, MB, and there's actually a unique ideal of index dB squared that basically comes down to the structure of quaternion algebras over local fields that, in general here, if you have a quaternion algebra over a Dedekind domain, if you look at maximal ideals of OB, they're actually in bijection with maximal ideals of just Z by contracting the ideal. So if you just think about the primes that divide the discriminant, there's a unique maximal ideal lying over it. And if you just take the product of those, we get this MB here. And it's index dB squared because if you just look at, if you just complete it at P, then you get the maximal ideal in the unique quaternion division algebra over QP. And that one, that maximal ideal has index P squared. I mean, if you mod out the OB by MB here, you get a product of the number of primes dividing dB copies of a field with P squared elements in it. Okay, and then we fix F to be the real quadratic subfield of this biquadratic extension. So you have like K, then you have your two imaginary quadratic fields, and you have your kind of F in the middle here, the real quadratic subfield. And then let D be, this capital D here, be the different ideal for F. Now, there's one technical assumption we make here to make things work later on, is we assume that each prime dividing dB is inert, meaning prime in K1 and K2, which, I mean, I always thought that this wasn't too bad to assume. It's kind of, it's an assumption about finitely many primes, so it's a reasonable, not too strong of an assumption. Just one other thing here, since we are assuming, I'm still assuming that K1 and K2 have relatively prime discriminants, so that guarantees that if you look at the ring of integers, the maximal order in K is just the product of the two rings of integers in K1 and K2. So that can be useful later on. Okay, so that's a setup. So now the main objects we're going to look at here are these things called QM abelian surfaces, which are, here's a definition. So I want to define it as over a general base scheme. So if you just start with any scheme, then a QM abelian surface, this is an abelian scheme of relative dimension 2, together with a ring homomorphism, like an action of this maximal order on A. So, I mean, mostly I'm going to be dealing with the S being in FP bar, so algebraic closure of a finite field. But I do want to, it's important to give a kind of general definition here. So just maybe a reminder what abelian scheme is. It's a group scheme that has, it's proper and smooth over the base, and the fibers are connected. So it's basically like it's a scheme over S where all the fibers themselves are abelian varieties. Okay, so it's a kind of an abstract object, but these things over the complex numbers are kind of very explicit, and there's nice kind of description of these things. So this is really the reason why did I choose B to be indefinite. I think this is kind of one of the main motivations for why we say that B should be indefinite, is because we get this embedding of B into M2R, and then we can kind of play with matrices here. So if we start with a number in the upper complex half plane, we look at this lattice, this lambda tau here, which is we just inject this maximal order into view it as matrices and hit it on this vector tau 1. We get a lattice in C2, and then we can form this quotient. We get this torus here, C2 mod this lattice. And then we have an action of this OB just through this injection here on this quotient. So then you can show, it's not certainly not obvious why that we can show this, that first, that this actually, I'm being a little bit imprecise here. This is the complex points of an abelian surface. So you have to show it has some kind of polarization, some kind of Riemann form on this torus, but you can show that. And we get an abelian surface, and it has this action. So it's a QM abelian surface. So it turns out that this is not like some kind of special example. It actually kind of parametrizes all QM abelian surfaces over the complex numbers. So the general result about this has been known a long time, which is that if you look at the 1 units here, all the units in OB that have reduced norm 1, and you take that and you inject it into M2R, quotient by plus or minus 1, we get a discrete subgroup of PSL2R. And then what you can do there, if you can take H and kind of mod out by this subgroup, then we get, actually, there's a bijection between that quotient and a set of isomorphism classes of principally polarized QM abelian surfaces over C by sending this coset to this pairing that we just defined up here. So let me point out here, I put principally polarized. It turns out that every QM abelian surface automatically has a principal polarization. I'll state that in a minute. So it's nothing kind of extra, but you do need to kind of keep track of the principal polarization to kind of have this as being a kind of correct uniformization here. So this is a kind of concrete example to keep in mind, that over the complex numbers, there's a very kind of explicit description of these things as these kind of quotients. Okay, so I want to talk a little bit about, in general, over general base scheme, these QM abelian surfaces. Like I said, the general fact here, again, this is nothing new. This has been around for a while. I mean, I think this is usually attributed to Milne, I think, this general fact here, that if you have a QM abelian surface, there is actually a unique principal polarization on it that induces this. So this left-hand side here is basically just a Rosati involution on the endomorphism algebra here. If we look at this composition here, it just induces this star I can't remember the name now, the star involution, excuse me, involution on OB there. So that in general, there may be more than one principal polarization. There's a unique one that has this condition. And that's important because I want to kind of come up with or define a notion of degree that kind of is a bit different than the usual notion of degree for morphisms. So like in general, if you have a finite locally free morphism on schemes, then you can define degree. Like if you have an isogeny on a abelian scheme, you can talk about degree. But I want a little more of a different notion of degree here that actually takes into account this kind of OB action. So if we start with two QM abelian surfaces here, and we look at the lambda 1, lambda 2, the corresponding principal polarizations from this general fact here. If we start with any OB, so this home here is your OB linear homomorphisms from A1 to A2, meaning homomorphisms as abelian schemes that commute with the OB actions at A1 and A2, then we can form this composition. If you do lambda 2 composed with this F check is the dual map on dual abelian schemes, and compose it with lambda 1 inverse, we now get a homomorphism from A2 to A1 going the other direction. And I'll call that in general the dual homomorphism or dual isogeny. So it turns out that if you take and you compose F with its dual, and so you can view that as an endomorphism of A1 that, at least locally on S, it's multiplication by an integer. So in particular, if S is connected, it itself is just multiplication by an integer. So I'm going to give a name to it, this degree star here. There's no standard name, at least I can tell, for this degree. I called it the QM degree in my paper, so just to give it some kind of name here. So you can show that this map, this degree map, QM degree actually gives us a positive definite quadratic form on this homomorphism group. And there's an easy connection between the usual notion of degree and this QM degree. It turns out that a QM abelian surface, the usual notion of degree, the degree of some homomorphism actually is always a square. So, and it's a square of the QM degree. So the QM degree squared is always the usual degree of a morphism. So it's think of it as some kind of like reduced degree in some sense. And it's kind of a nice consequence of this is that actually this is unique to these QM abelian surfaces. This is certainly not true for any abelian scheme, that any non-zero element of this home group actually is an isogeny. And that basically comes from the fact that if you look at this composition here, F dual composed with F, that's multiplication by an integer. So that one we know is an isogeny. So that means that the second one here, the F transpose, that one's an isogeny, or surjective at least. And since the two abelian schemes have the same relative dimension, it has to be surjective. It's an isogeny. And so F transpose an isogeny, if you just dualize again, you get back the original F, and that happens to be an isogeny as well. Let me just point out a little bit how this works here in terms of proving this kind of result. Why is this an integer? You can just check that if you look at the Gross-Zagier involution that's an involution, positive involution on this endomorphism algebra. When you tensor this with Q, if you apply that positive involution to this object, this F transpose composed with F, it always fixes it. It's a basic calculation. And if you look at the fixed points of the Gross-Zagier involution, you can show that they're always going to be rational numbers. So, and also it's integral here, so it has to be an integer. And the way you do that basically is you look at the possibilities for the endomorphism algebra here. If you tensor this, like any QM abelian surface here with Q, there's a limited number of possibilities as to what that structure could be. One possibility is that endomorphism algebra could be Q, it could be an imaginary quadratic field, or it could be a definite quaternion algebra. And in each of those cases, the Gross-Zagier involution ends up being, so for Q, obviously it's the identity, imaginary quadratic field, just conjugation. And then for a definite quaternion algebra, the positive involution on a division algebra is going to be the main involution. So it has to be, the fixed points are just Q again. So that's why all the fixed points are just going to be in Q here. And that's why you get this kind of integer. Okay, so we have this kind of refined notion of degree. Now we're going to focus on kind of CM points here, which are, we have beyond just the QM action, we're going to look at an action of our imaginary quadratic field as well. So again, we start with a base scheme, but we're going to assume now it's an OK scheme. So it's S starts with some morphism, the spec OK. Just we'll see in a minute why I'm using this. So in general here, a QM abelian surface now with complex multiplication by, let's say, OKJ. It's a little annoying here. I kind of carry through. It's a bit kind of, the notation maybe is not the best, but I'm going to carry through this like this J, which is either 1 or 2, depending on whether you choose K1 or K2 throughout basically everything here. You can make this look a little bit nicer if you just say, okay, I'm going to fix one imaginary quadratic field, but that introduces kind of more notation. I just want to stick with the K1 and K2 we started with at the beginning. So this is going to be a QM abelian surface together with now an action of the ring of integers in KJ. And we're going to assume that this action commutes with the OB action. So you have these two commuting actions of OKJ and OB on the surface. And then there's some kind of extra condition here. This is like some kind of normalization condition where we're going to assume that the action of OKJ on the Lie algebra of A is through the structure map, meaning if you take and you just look at the inclusion of OKJ into this OK, which is, remember, is the composite of K1 and K2, and then map through the structure map because we're assuming it's an OK scheme, we're going to assume that the action here kind of factors through the structure map here. Now, it seems kind of like, why do we do that? I mean, you've probably already seen things like this in the past. Have you ever looked at like the theory of like CM elliptic curves? There's usually some kind of normalization condition given on the CM action. If you look, I've seen it presented as if you look on Silverman's second book on elliptic curves, there's this chapter on complex multiplication, and he talks about this kind of normalization condition where, like, if you take an element of OKJ and you kind of pull back the invariant differential, it just gives the multiplication by that element of OKJ. So some kind of normalization condition. And the reason why that, at least for elliptic curves, why it's important is it guarantees that the ideal class group acts simply transitively on the set of isomorphism classes of CM elliptic curves. So we're going to have kind of similar thing later on where we're going to use this kind of normalization condition. It actually guarantees that these like what I'll call CM-QM abelian surfaces lift uniquely from characteristic P to characteristic 0. So it's an important condition used in kind of lifting from characteristic P to 0. So we'll see later on that is an important kind of condition to include. Okay, so those are kind of the main objects we'll study, these QM abelian surfaces that also have an action of this imaginary quadratic field. Sorry, kind of a lot of stuff here. So the moduli spaces we're going to look at here, we're going to start with this I'm going to call MB, which is, okay, there's some technical stuff here that if you don't know what it means, it's not really that important. We start with this, which I'm going to call groupoid, which really just means also called a category fiber and groupoids over, it's just a category, think of it that way. It's a category over spec OK, where the fiber, meaning MB of S over a specific scheme S, it's going to be the category of all QM abelian surfaces over, I'm going to do it over some OK scheme S. And then again, there's some kind of normalization condition here where we're going to assume that at least locally on S, the characteristic polynomial of this I of X acting on the Lie algebra is basically the reduced characteristic polynomial of the element X. It's usually called the Katowitz condition, which is it's just really included to give a nice proper moduli space. It guarantees that the moduli space is going to be regular and it's smooth over the base when you invert the discriminant on the base. So it just guarantees some kind of nice properties. And it turns out that for the CM abelian surfaces we're going to look at, this Katowitz condition is automatically satisfied. So it's not too much to worry about here. All right, so that's the kind of general moduli space. We look at, this is our kind of analog of the integral model of a modular curve that we looked at the beginning. And then we look at these YJB, which is going to be our moduli space of QM abelian surfaces with complex multiplication by OKJ, how we defined it in the previous slide here. Okay, so this is a moduli spaces. Again, a technical thing here. These are Deligne-Mumford stacks, which you don't have to really worry about what that actually means. A finite type over spec OK. The important thing is that the MB has dimension 2, this YJB has dimension 1, and in particular, actually, there's something stronger here. This YJB is actually finite étale over spec OK, which, again, it's not super important, but just to mention that. If you don't like the idea of stacks, you can always view these as the corresponding coarse moduli schemes. They all have coarse moduli spaces, and you can just view them as schemes if you want to. So the main thing we're going to calculate here in the end to kind of generalize this Gross-Zagier formula is this arithmetic degree. So you can view these Y1b and Y2b as divisors on MB. Really, the way we can do that is that there's a morphism from YJB to MB. If you just forget the complex multiplication structures, the forgetful morphism for each of these, then we can, through their kind of stack theoretic images, we can view these as being divisors on this surface here, this MB, and we can then define their intersection multiplicity, also called arithmetic degree, the intersection or Erich-Kalov degree of the intersection, through this kind of definition. It's kind of an odd, looks kind of like an odd definition, why we define things like this. There are kind of bigger kind of reasons why these things are defined this way, which are probably not important for what I have to talk about. I mean, the motivation, I think, for this definition comes from intersections on arithmetic surfaces, which is something that I don't really know enough to really explain as to why it's defined this way. I kind of took this as just kind of given to me, which is what we do here is we sum over all the prime ideals of OK. And then there's some log term here. Again, that's coming from some arithmetic intersection theory, which you don't have to really worry about for this application. And then what we do is we sum over this bracket here means isomorphism classes. This just guarantees that we're summing over an actual set as opposed to a category. So we're summing over all the isomorphism classes of geometric points, and we look at the length of this ring here over the automorphism group of the point. So what is this ring here? This is the local ring of the moduli space for the étale topology. So what this really is, it's this SH it's a strictly Henselian ring. So it's a ring where Hensel's lemma is satisfied. The strictly means it has separately closed residue field. I mean, the residue field is just going to be FP bar here. And the way you define this is you just look at all what are called étale neighborhoods of the geometric point, this X. So if you look at all schemes over the moduli space that are étale over it, and you look at geometric points of this étale neighborhood here, and you look at, if you just take the image of a geometric point of your kind of étale scheme over the moduli space, and you look at just the image of that geometric point in the scheme, and you take the limit over all the étale neighborhoods of the local ring of that étale scheme over the moduli space. This is what this ring is. Again, the actual definition of it, it's not super important for what I have to say. I mean, I'll explain later on why we can, there's a bit easier way of viewing this. And then, of course, I should have said here, this FP is just the residue field for the prime P. Okay, so the main result here is going to be a formula for this intersection multiplicity, but maybe a little bit more general here, not just this one. I'm going to actually look at the intersection multiplicity here of, if we take this, what's called the Hecke correspondence applied to the first divisor intersect with the second one. So what does this mean? I mean, there's this Hecke correspondence. Really what we're doing here is, if you look at the space of all triples, where we have, let's say we have like A1, A2, two QM abelian surfaces, and you have F, some morphism between them of degree M, then we have, from that space, you have a projection down to just M, it's MB itself. We're just projecting onto the like A1 and A2. If you take a divisor on MB and you pull it back and then push it forward from that moduli space of the triples, that's what this TM, this Hecke correspondence is. Again, the actual definition is not super important. All you really have to worry about or think about here is that this intersection, or this kind of intersect these divisors, it basically corresponds to the space of triples where you have A1, A2, and F, where A1 and A2 are two QM abelian surfaces with CM, and F is a morphism between them with QM degree M. So it basically classifies pairs together with a morphism between them of a specified QM degree. And that's what we're going to try to find this kind of arithmetic degree of. And we'll see that this actually does kind of generalize the Gross-Zagier formula in the end, explain how that works. Okay, so that's the setup here. Now, one of the kind of key things that we're going to use in that I did use in proving kind of the formula for that intersection multiplicity is a kind of a structure theorem for these QM abelian surfaces. It turns out that every one of these, at least the CM QM abelian surfaces, arises from an elliptic curve. So basically every surface comes from an elliptic curve through some kind of tensor product. And the way this works, it's a bit kind of technical here, but it's, if we start with, let's just look at these two sets here. If you look at this, just kind of just sets of algebraic objects. If you look at these ring embeddings of OKJ into OB, the OB cross conjugacy classes of these things, and then you also look at these isomorphism classes of modules over OB tensor OKJ, let's say rank 4 over Z, there's a bijection between these algebraic objects by sending a ring embedding here to basically just OB viewed as a module, OB module on the left through multiplication, and a module over OKJ on the right through this ring embedding, this theta. Let me also point out that these two sets are also in bijection with the complex points of this YJB, meaning the CM points over the complex numbers by descending one of these modules to the abelian surface that has complex points by just kind of taking the R span of the module that's a four-dimensional or two-dimensional complex vector space and dividing out by this module here. Now, the reason why I wanted to state this result is because later on I'm going to have these kind of ring homomorphisms from OKJ to OB kind of going around, and I want to kind of at least motivate as at least a little bit where these things come from. Why are we talking about these ring homomorphisms? So what we can do is if you start with just these ring embeddings here, I can actually kind of refine this set a bit further by defining an equivalence relation on this by just saying, okay, I'm going to actually instead look at maps from OKJ to OB mod that ideal, the unique ideal of index dB squared. And I'm going to say that these two ring embeddings are equivalent if they induce the same map on this quotient. Okay, so here's the general kind of structure theorem. And so this is something I proved. I think this is a new result, which is that if you just look at Yj being the stack of all, it's the kind of moduli space of all elliptic curves over OK seams with CM. So again, an elliptic curve with CM has this normalization condition that the OKJ acts on the Lie algebra through the structure map. Okay, so then if we start with any kind of OK base scheme, any CM-QM abelian surface arises as a tensor product here of one of these modules together with an elliptic curve. So what does this tensor product mean? How do you tensor a module and like a scheme like this? There's this thing called Serre tensor construction, which is if you can take any group scheme that has an action of a ring and finally generate projective module over that ring, and you can tensor the module and the abelian scheme by just a general kind of categorical construction, which is it's the unique group scheme that has its kind of t-valued points being m tensor e of t. So you basically just do it in the kind of most obvious way. So some way of tensoring a module in a group scheme to get another group scheme out of it and get another abelian scheme out of it in particular. And just in terms of kind of dimensions here, if the m is projective of local dimension, let's say n, and your abelian scheme here as relative dimension m, then the tensor product has relative dimension n times m. So if you think about this at least kind of works out in terms of dimensions. The m is projective of local dimension, locally free of rank 2 here over OKJ, and E it's an elliptic curve, so it has relative dimension 1. So the product at least has relative dimension 2 over the base scheme. And so that's very useful. You can basically, what I do is I can use this to kind of use arguments from elliptic curves to kind of bring it up to the level of these abelian surfaces. There's a more technical result here, which is that we can actually get a kind of decomposition of this moduli space of the CM-QM elliptic of abelian surfaces as a disjoint union here of these moduli spaces of elliptic curves, which is you basically just map an E to this tensor product. So there's some decomposition in terms of stacks here, but again, that's not super important for what I have to say here. It's just the main thing, the result of this is that every CM-QM abelian surface arises from an elliptic curve, which makes things much easier in terms of the actual results later on. Okay. So I want to get to this main theorem here, which is, I'll get to that soon, but the main, a couple of things I need to state beforehand, which is that instead of looking at just this kind of QM degree, I want to refine that a little bit here further, because it turns out if you just look at the pairs together with a morphism that has QM degree some number m, we're still not going to get it. We want a zero-dimensional stack here. So for this to make any sense, to do like an intersection on a surface, we need the two divisors to intersect transversely, which means give it a zero-dimensional stack here, zero-dimensional moduli space. So the way we do this is we kind of refine the notion of degree a bit further here, which is if you start with, again, a CM/QM abelian surface, there's actually a unique quadratic form on this homomorphism group here that has values in the inverse different. And this is just basic linear algebra. There's a unique the quadratic form above the QM degree, who's traced down to the to to Q here from F to Q gives us the QM degree. So just kind of basic idea with linear algebra here. All right, so now the main object, the main kind of moduli space we're going to look at is, again, this involves some kind of, it's hard to motivate as to why we do this, but we look at least I hopefully did with the last slide here, we look at some ring homomorphism from OK to OB mod MB, and then we look at the moduli space here of triples where we have two CM, QM abelian surfaces and a morphism here. Down here, F is a morphism between A1 and A2 that satisfies that QM degree, excuse me, it's CM degree, this kind of more restrictive notion, refined notion, is this number alpha that we start with on every connected component of S. And then I introduced one extra kind of normalization condition here, which again, it's similar to like the CM condition in that it's useful later on to prove certain properties of this moduli space. And what do I assume here? I look at where does this theta come in? Well, if you restrict theta to this OKJ, it gives a map from OKJ to OB mod MB. And I say that the first thing is what is this bracket MB? This is just the MB torsion. It's like you define any kind of torsion on the abelian scheme. You can define its scheme theoretically as the intersection of all the kernels of I of X or X ranges over MB. So it's some finite flat commutative group scheme over the base. And so you have this torsion, and then there's an induced action of OKJ on this torsion. And my kind of restriction here is that I want the OKJ action to factor through this ring homomorphism. Sorry, need to go back here. Theta. Let me just point out that over an algebraically closed field, if S is an algebraically closed field, this endomorphism ring here is actually isomorphic to OB mod MB. So there's automatically a commutative diagram like this. So what I'm doing is I'm just kind of keeping track of how does OKJ act on this MB torsion, just kind of keep track of the action through this ring homomorphism theta.
Andrew, there's a question in the chat
Oh yeah,
about the
sorry. Yep.
quotient OB mod MB, so if this is a field or what's this
Oh,
structure?
okay. So yes, MB was the unique. I wrote MB, but it's not actually a maximal ideal. It's a product of maximal ideals. MB is the product of the unique maximal ideals of OB for each prime dividing the discriminant. So the structure of OB mod MB, it's a product of, let's say, R finite fields. R is the number of primes dividing the discriminant. It's a product of like FP squared, finite field of P squared elements, R copies of that finite field. Okay, so what that tells you is that if you take any ring homomorphism from OKJ or OK, let's say, to OB mod MB, it's the kernel of it is going to be a product of R prime ideals, where R again is the number of primes dividing the discriminant. So it's a product of R finite fields of P squared elements. Okay. Could at least say this. So looking at our moduli space here, sorry, I'm gonna go back. This is the moduli space we care about here, the space of these triples. So let's just look first at geometric points, meaning if you take K to be an algebraically closed field, what kind of objects, what do these things look like over algebraically closed fields? Well, it turns out that there has to be, we only have geometric points in characteristic positive P. So this moduli space does not have any geometric points over the complex numbers. And in particular, actually, if K is FP bar, which is merely the most important case for us, then we can say that the QM abelian surface actually has to be supersingular, which means it's isogenous to the square of some supersingular elliptic curve. So the key point, the reason why, if you go back to that definition of the arithmetic degree, there was a reason why I didn't sum over like all geometric points. I only summed over FP bar. It basically is because this moduli space we're going to look at doesn't have any points outside of characteristic P. I gave a little sketch of this, but I don't think I have time to go over this. So just the basic idea is that we can't have points in characteristic 0 because if you have a isogeny between A1 and A2, it induces an isomorphism between the endomorphism algebras. And we already know that there's CM structure, so there's K1 and K2 embed into these algebras. And just the general result about these QM abelian surfaces, and over the complex numbers, this endomorphism algebra is either Q or an imaginary quadratic field. So if Q obviously is impossible, and if they're imaginary quadratic, then we get K1 isomorphic to K2, and we're assuming that they're non-isomorphic. So it only has points, only has geometric points in characteristic P, and they have to be supersingular, which is just kind of interesting here. Okay, I want to get to the main theorem. So I know there's just kind of like a lot of setup to this. I kind of understand the kind of a lot to keep in mind here, which is just a little bit more here, which is that the main theorem is going to involve just some notation here. This chi is the quadratic Hecke character associated with K over F. So if you have some quadratic extension here, there's a character on the Idel class group that's associated with it, and we can view that character as so basically what it looks like is it's a product of local characters. It's a quadratic, so it has image in plus or minus 1, and it basically tells you locally is the element that you're plugging in a norm or not a norm, going down from like KV down to FV for each place of F. So it's kind of like a local norm condition, local norm check here. And you can view this since I'm assuming that the discriminants of K1 and K2 are relatively prime. That guarantees, it's important here, that guarantees that K over F is actually unramified at every finite place. So that also guarantees that we can view this character as a character on ideals, basically just by looking at generators, local generators of ideals, since it's an unramified extension. The other important notation here is that the row of A, if you start with a fractional ideal of F, row of A is just going to be the number of integral ideals of K whose ideal norm is little a. So obviously, if you look at this here, this number will be 0 if the ideal that you start with is not an integral ideal. So if your little a is not actually contained in OF, there's certainly not going to be integral ideals lying over it with norm that ideal. So we have this function. I want to state it more generally because it's potential. I want to allow for the possibility for that to be equal to 0. And then one more kind of set here. This is basically going to form the support set of our stack, which is we're going to look at all primes of F, whose, again, this is the kind of the local character at P. When you evaluate it at some alpha is an element of F. Alpha times this A theta D is equal to -1, where A theta here is the kernel of this ring homomorphism contracted down to F. So you can show that this set has odd, it's finite, basically from just considering finitely many primes that divide these ideals. And then you can also show that it has odd cardinality using the product formula for Idels. And so in particular, it's non-empty. That's the important thing. Okay, so here's the kind of thing that I want to compute in the end. Just a reminder of what this degree looks like. We're summing over all primes of OK, and then summing over here all geometric points over this FP bar, the length of the local ring over the order of the automorphism group. So just to point out here, this group is certainly finite Because if you just think about this, what do automorphisms look like for these like pairs A1, A2? They're just going to correspond to like pairs of units in K1 and K2, and there's finally many of those things. Okay, so here's the main result. We can look at this for a minute here, which is we want to start with an element of D inverse different and assume it's totally positive. The reason why is because that remember I said before that QM degree was always sorry, the CM degree, the trace of that gives you the QM degree, which is always a non-negative integer. So we're going to always have to start with something that is totally positive for this to make any sense. So at least to give something that's a non-empty stack here. So let's suppose that this diff set that I defined in the last slide here, it's basically the support of the stack. It consists of just a single prime. Just let's start with that assumption. And let's let little p be the prime below p in the integers. So it turns out that this stack remember the stack of triples where it's A1, A2, F, or A1, A2, QM, CM, QM abelian surfaces, and there's some morphism between them using of CM degree alpha. And then this theta gives you this kind of normalization condition on the MB torsion. This is a dimension 0, meaning these local rings, the strictly Henselian local ring is a 0-dimensional ring. And it's supported in characteristic P, meaning all geometric points have to be characteristic P. That's what I went over a few minutes ago. So there's an explicit formula here for this degree. And you can see here, I think the thing to notice here is that there's different cases to consider. There's, depending on whether the prime divides the discriminant or not. And then also if you look at this capital P, which is the prime in K over this P and F, does that prime divide the kernel of this theta or not? There's different formulas based on that. And then if your alpha is not in the inverse different, or if this diff set, this is probably the most interesting thing, if this diff set has cardinality greater than 1, then actually the stack is empty, doesn't have any geometric points, which is kind of interesting here. And then there's a decomposition here, just to kind of answer the original question I was going over. There is a decomposition here of this kind of intersection multiplicity of these two divisors in terms of these degrees. So once you have formulas for these degrees, then you'll have a formula for this intersection multiplicity. Let me just point out that there are many examples of theorems like this already kind of in existence. Generally, this formula for the degree is only like half of these theorems. Usually there's another half where they show that this degree is equal to some Fourier coefficient of a derivative of like an Eisenstein series or something like that. Like for example, the more famous Gross-Zagier formula on relating the derivative of an L series to this kind of heights of Heegner points. That you think of that as an example of the theorem where you're kind of relating some arithmetic quantity to some analytic kind of Fourier coefficient. There's probably a theorem like that for this situation. I haven't looked at that yet. I just looked at the algebraic side of this, but just be aware that there's probably a way of getting a kind of more general theorem like that. And then let me just point out that in the case, if you take B to be just M2Q, if you just take the split case, then that actually recovers basically like there's an elliptic curve. I generalized the elliptic curve analog, the elliptic curve situation here. If you look at these spaces for elliptic curves instead of QM abelian surfaces, there's already a theorem, that was what I was generalizing, by Ben Howard and Tonghai Yang. That is kind of a generalization of that theorem. And you can actually recover the Gross-Zagier formula as a kind of a special case. So like in the P not dividing the discriminant case, you can, if you kind of suitably kind of interpret these things, you can kind of recover the Gross-Zagier formula from the P not dividing the discriminant case. Okay, so let's see. Let me just finish up in the next minute here. So just the general kind of summary here. The proof, it takes a lot to kind of prove this. There's kind of a lot of technical stuff that goes into it. Basically it amounts to two general parts. there's counting the geometric points and the calculation of the length of these local rings. Um, Probably the counting geometric points is more difficult. There's a lot of technical calculations. But the nice thing is that it's a lot of basically like linear algebra. It comes down to just looking at like I kind of develop explicit coordinates for due to A modules and just do like calculations with matrices. And there's a lot of kind of basic kind of linear algebra calculations that go into it, which is interesting. Now, the length of the local ring, even though it's a kind of it requires more background knowledge, it actually ends up being a bit simpler in that it basically uses deformation theory, this like growth and messing deformation theory, where we look at kind of lifts of your kind of points on over FP bar, lifting them from characteristic P to characteristic 0. Just kind of one interesting thing. There's some like actions of certain groups that you look at here. Let me just skip that. Just one interesting thing to finish on, which is that actually this reduction map, you take sorry, put a B on this. If you look at the reduction if you take for example, you take like complex numbers and kind of reduce, kind of descend to a number field and reduce mod a prime and base extend to FP bar, that kind of reduction map actually is a bijection. You can uniquely lift a CM-QM abelian surface in characteristic P to characteristic 0. And the key fact there is using that kind of that CM normalization condition I mentioned earlier on. So yes. Okay, that actually ended up being a lot longer than I thought to explain all this stuff, but I had more to talk about, but I don't want to go too long here. So maybe I should actually just stop at this point.